So we're moving into three-dimensional structures. Three-dimensional structures in chemistry is referred to as stereochemistry. What we're going to use as our model, and this whole unit is based on models, based on Lewis symbols or Lewis dot diagrams, using representative elements, S and P orbitals. Okay. Our theory here is going to be VSEPR. Valence shell, so those are those outermost electrons. That's, you know, kind of using Lewis symbol type theory. So the valence electrons, okay, we've been talking about pairs, lone pairs and bonding pairs, and this theory just uses maximum repulsion to predict the bond angles. So if you have two pairs of electrons, they're going to want to get as far apart from each other as possible. So we've two pairs of electrons, the furthest they can be is 180 from each other. So that's what VSEPR theory is going to predict. Okay. Now, we're going to have to keep in mind it's three-dimensional repulsion, not two-dimensional. So when you repel four things in three-dimensional space, you don't get 90, 90, 90. That would be if you're on a plane. So what are some pieces of this theory? So it's kind of already been mentioned in explaining the wording. Okay, it's only the valence electrons that affect the shape around a central atom. This will kind of keep coming up. We're going to do shape or shapes, plural. If there are three central atoms, we're going to have three different shapes. We're going to have to look at them one at a time. The theory treats all electron pairs as being approximately the same. We'll tweak this at the end of the lesson and realize there's subtle differences between lone pairs and bonding pairs. But right now, they're all going to be the same. So if we have a carbon with a double bond to another carbon, we're going to treat all our groupings of electrons as being the same. So we've got a group there, a group there. Now we have two groups here, but we're going to lump those together as our third grouping to predict the shape. Okay. So we're going to treat lone pairs the same as bonding pairs, whether they're a single, a double, or triple. We're going to treat them as one grouping. Okay. Electron pairs will repel each other. Groups of electrons are going to repel other groups of electrons, and the shape maximizes the distance between the electrons. So I'm just going to go a little bit deeper, or connecting to yesterday. Sort of relating back to hybridization. In particular, connecting to carbon. If we have four groups of electrons, that'd be what we would see in something like methane, carbon with four bonds. Whenever we have four groups of electrons, we needed four atomic orbitals to be mixed together to make that. Okay. So we're going to have S, that's one orbital, and then we need all three of the P's. So we're going to have sp3 hybridization. We're going to have four things spread out in three-dimensional space. So we don't get 90, 90, 90 because it's spread out in three dimensions. We get that 109.5 bond angle. So anytime we have 4 groupings of electrons, we're going to get this hybridization in that bond angle. You don't really need to know what the hybridization to do this. You just have to know that there's 4 things connected to it. Okay? It's a bit of an extension to know that hybridization. Okay? If you have 3 groups of electrons, now I've got 2 carbons, so I'm going to put an arrow referring to a central atom. Okay? That central atom has 3 groups of electrons. 1, 2, and then the third grouping is a double. Okay? Now this is going to come from those 3 groupings of electrons are going to need 3 atomic orbitals to make the first bond in each of those groups. So 3, 1s, and we're going to need 2 of the p's, and then there's another p left over. And that's why we have the double. How it always works out is the very first bond, which I'm going to go and recolor code my bonds black, is always a hybridized orbital. It's coming from sp, sp2, or sp3. And these are called sigma bonds. The first bond is always a sigma. Left over p orbitals, those are what make our second and our third bonds, and those are referred to pi. Now in chemistry 30, which I happen to be doing in another class right now, we're talking about, this is a regular 30, and we're talking about organic chemistry reactions, and I'm telling them that that second and third bond is a different type of bond and really weak. Okay? I'm not going to tell them that they're necessarily sigma and pi, but this second bond is really weak and can break easily. So there's a second bond. So I'm making that purple. That's one of those weaker pi bonds. All the other first bonds are sigma, and they're coming from hybridized orbitals. I'll do my last example, I can color code them a little nicer. So if you have just 2 groups of electrons, you'd see this when you have a triple bond. Again, there's 2 central atoms, so I'm going to talk about the one on the left. Okay? There's a single and a double, that's the 2 groups. So that's going to be a straight line, it's going to be a 180 bond angle. Okay? When we had the 3 groups, we get 120. Here we get 180. What's the hybridization? Well, there's 2 different groups of electrons. We have to hybridize 2 orbitals, an s, and we only need 1 of the p's. That leaves 2 p's left over, which leads to 2 extra bonds. So the first bond between the C, or the only bond between the C and the H, is one of these sigma bonds from a hybrid orbital. The first bond of the triple is a sigma, and the next 2 are pi's. So just color coding these. That's our sigma bond, the first one. One of the leftover p's makes the double, the other leftover p makes the triple. So kind of going backwards. First bond is a sigma, the second is a p orbital of pi, the third bond is a p orbital and a pi. You can kind of work backwards and get the hybridization instead of kind of working forwards the way we did yesterday. So we're going to get all our shapes based on this. So let's start running through those 5 shapes that everybody needs to know based on grouping of electrons. So first shape we're going to go through is linear. Okay. You're going to get this in 2 different circumstances. Okay. You have a central atom has 2 bonds and no lone pairs, or the central atom only has 1 bond. So it'll have to be a straight line. So the top line is a bit more complicated. I'm going to draw out a bunch of examples of a central atom with 2 bonds and no lone pairs. A central atom bonded to one thing. That we're going to cover quickly. You're rarely tested on it. That'd be like H to F. There's only one bond, well then it has to be straight. That's kind of boring. I'm going to be using bonding capacity to put together pretty much all of my examples in this lesson. So group 4 has 4 bonds, group 5 has 3, nitrogen, oxygen, group 6 has 2 bonds, group 7 has 1 bond, and we're not going to see any noble gases. So carbon dioxide is a linear molecule. We would take the single atom and put it in the middle. Carbon wants to have 4 bonds. Oxygen would want to have 2. So if we think of this oxygen atom, it wants to have 2. It doesn't really have any choice but to do the 2 right with the carbon. You know, carbon wants to have 4 bonds, and there's 2 O's, so 4 divided by 2 is 2. You end up with a double each way. So carbon has its octet. Its 4 bonds go 2 to oxygen, 2 to oxygen. This oxygen would have 2 lone pairs left. Oxygen has 2 lone pairs, 2 singles. Now, a structural formula shouldn't have the dots, but I'm always going to put the dots in because we need them for our pairs to know about shapes. So that's why you're encouraged to put them in. The shape comes from looking at the central atoms. We actually can ignore the dots and those O's because they're not on the central atom. Okay. How many bonds do we have on that carbon? We have 2 bonds, and there are no lone pairs. So we're going to get a straight molecule. So that's how regular 20 would look at it. Okay. We could reinforce that, add to it, okay, by looking at the hybridization. Okay. There are 2 bonds, so we'd call that sp hybridization. Okay. There are 2 leftover p orbitals. One makes the double on the left, one makes the double on the right. Okay. So whether you think of this from the hybridization or you just count 2 bonds, no lone pairs, you're going to get linear either way. So you kind of have 2 methods to tackle to get the right shape. So that's carbon dioxide. Beryllium dihydride. Beryllium's in group 2. It has would have 2 dots in its Lewis symbol. Beryllium wants to form 2 bonds, and that's why there's 2 H's. Beryllium has no lone pairs. If it did, it wouldn't be straight, but the absence of lone pairs makes it linear. 2 bonds, no lone pairs. It's hybridization. There's 2 bonds, so it is also sp. It just doesn't have any electrons to put in leftover p orbitals. Because those leftover p's are empty, we don't get any double bonds. But again, you don't have to use hybridization. You can just go 2 bonds, no lone pairs. These are linear. These are 180 degrees. So that's our first shape. Okay. 2 bonds, no lone pairs, or just 2 atoms. We're going to move into trigonal planar next. We could tackle this from hybridization, but every 20 would want to think of this as 3 bonds and no lone pairs. So my first example will be C2H4, 2 carbons and 4 H's. You could use bonding capacity to put this together. You're definitely going to put the carbons in the middle because you're not going to put a bonding capacity of 1, the hydrogen's in the middle. Okay. I'm going to connect those carbons up, and then we've got 3 bonds left on each carbon, but only 4 H's. So 3 bonds each would be 6, but only 4 H's, so we can't put all the H's and fill up all the bonds. We're going to have to make a double. Okay. So hopefully you're starting to realize that double is caused by a leftover p orbital. So now there's 2 bonds left on each carbon, and that's where the 4 H's can go. All of those black bonds are hybridized bonds, the first bond to each atom. Okay, so there are 3 total bonds. Again, I have to think of, from that carbon, there are 3 bonds around it. So this is going to be trigonal planar around that carbon. Okay. Trigonal planar is 120 degrees, 3 things broken up in 3-dimensional space. There'll be 120, 120, 120, and flat. Okay. The black bonds are sigmas, that red bond is a pi. The hybridization, there's 3 groups of electrons, so sp2, okay, to get the 3 black bonds. Now, if we look at this carbon on a test, I might ask you, what's the shape of every central atom? And it's the exact same thing. There are 3 black bonds and then a leftover p, 3sp2. So that's also trigonal planar on the other side. So both of those carbons are 120. There's no lone pairs. A second example, this is going to be one of the few times that you'd have to use the 5 steps, but nitrate, NO3-, also has the same shape. Now, I'm not going to go through all the 5 steps. I'm just going to draw the outcome. But if you count up the valence electrons, put the N in the middle, put all the O's around it, connect everything up, build an octet on the outside, then get an octet on the inside, you end up with 1 double bond being formed. Now, because this is an ion, I need to square bracket it and put the charge. Now, what we care about is the shape. 2 ways to get to the same answer. If you just use regular Chem 20, there are 3 bonds around this nitrogen. There are no lone pairs on the nitrogen, so we would expect a 120-degree bond angle. We would expect trigonal planar. The 3 bonds are single, single, double. Okay. We could also use the hybridization. There is 1, 2, 3 first bonds. Okay. This double is up from a p. So 1, 2, 3 bonds. So we'd have to mix 3 orbitals. So it's sp2 and a leftover p cause the double. Keep going. Tetrahedral. So the theme has been 2 bonds, no lone pairs, 3 bonds, no lone pairs. Now we're at 4 bonds and no lone pairs. We're going to have to stop this trend because we can't have 5 bonds and no lone pairs. Because we only have 4 orbitals. And none of the shapes have expanded octets in chemistry 20. So 4 bonds, no lone pairs. We've already seen this in our notes today. We've seen in the past. Methane. Carbon loves to have 4 bonds and no lone pairs. As long as there's no doubles or triples with the carbons, you're going to get a tetrahedral shape. So tetrahedral is kind of the 3-legged stool. 3 down and 1 up is what we get with 4 bonds and no lone pairs. In 3-dimensional space, we get 109.5 as that bond angle between all of our atoms. So carbon. So obviously what I'm drawing isn't the true bond angles. It's not flat. I'm taking the three-legged stool on the bottom and I'm squishing them all flat for the sake of a flat board. But those bottom H's, the two on the right and the left, are really behind the board, and the middle H is out of the board, is the front leg of the stool. Two ways to think of this shape. Okay. It's got 4 bonds, no lone pairs, so it's 109.5. It's tetrahedral. Or if you think of its hybridization, there are no p orbitals left over. There are 4 bonds. You need 4 orbitals, sp, and you need all 3 of the p's to get your 4 bonds. A second example from an ion that is sp3 hybridized or has 4 bonds and no lone pairs is ammonium. The IUM is NH4+. This was in our ion example lesson. So there's nitrogen, 5 electrons, 4 H's, 9, but it's positive, it lost 1, 8 electrons. So we have nitrogen as the central atom. When you connect the 4 H's, you use up all 8 electrons. So there's no need for a lone pair on that nitrogen. There's no electrons left. And this has 4 bonds and no lone pairs. Or the 4 bonds leads to sp3 hybridization. Either way, tetrahedral, 109.5. So fourth shape, trigonal pyramidal. We finally have lone pairs. This is where you need to be drawing them in or understanding they're there. If you have 3 bonds and then another grouping of electrons, okay, this would be 4 pairs of electrons. But the electrons don't show up in the name. Now we saw 4 pairs of electrons. What was that bond angle? When did we have 4, but they were all bonds? Let's flip back. Oh, that was tetrahedral we just did. Had 4 groupings of electrons. They were just all bonds. We still have 4 groups of electrons, but it's 3 bonds and the 4th is a lone pair. So we have that exact same shape of electrons. The electrons will still be 109.5, but the top isn't a bond anymore. So we call it a pyramid. So if you think of tetrahedral and you pop the top off, you got a pyramid. Okay? But the lone pair on the top keeps the 109.5. So let's look at some examples. Ammonia is going to be like this. Now nitrogen has a lone pair and 3 singles. Those 3 singles kind of make those 3 legs we saw before, but the top doesn't have a bond. The angle between any of those electrons would be 109.5. Okay. We get the same bond angle. If we think of this from a hybridization perspective, there are 4 groupings of electrons. There's no double or triple bonds here. To get the lone pair and the 3 bonds, the 4 groupings, you need sp3 hybridization. We don't call it tetrahedral because we don't factor in the lone pair in the naming. In molecular geometry, we name the molecules. We don't name the electron shape. No, there's a lot of patterns to this unit. What bonds like this? You know, what atoms, question mark, have a lone pair and 3 bonds? Everything in group 5. So if you get comfortable with how nitrogen bonds, well, phosphorus bonds the exact same way. Or if you had bonding in arsenic, it'd be the same. Now, as you go down, you're going to get into metals. You're not going to see sharing of electrons likely, but nitrogen and phosphorus. When you get to exams after you've practiced, there'll be questions you wouldn't even draw. I put phosphorus trichloride on an exam. If you remember how nitrogen bonds, and you realize, okay, phosphorus is the same as nitrogen, and chloride is the same as hydrogen, it's also going to be trigonal pyramidal. Or I do phosphorus triiodide. It's the same shape. Okay. Many of you won't even draw it. You'll just realize the patterns. Okay. The same way that carbon and silicon bond very similarly. Carbon and silicon are both in group 4. So CH4 and Si, 4 H's, are both going to be tetrahedral, 109.5. Okay. Nitrogen, phosphorus, oxygen, and sulfur are going to bond exactly the same. We only have one left. We're kind of working our way down. We went from 1 up with our bonds. Now we're going up with our lone pairs, 2 bonds and 2 lone pairs. There's a few words you're going to hear. I would accept bent, angular, V-shaped, any of those terms. This is the shape you get wrong if you don't realize about the lone pairs. You don't understand water if you don't realize there's lone pairs on the oxygen. So oxygen, as our central atom, has 2 lone pairs and 2 bonds. Okay. And then hydrogen has 1 bond. Those lone pairs prevent it from being linear, like we would have seen in beryllium dihydride. The bond angle we'll get from thinking of the hybridization. A regular 20 would just have to memorize what I'm about to say. You've got the hybridization as a bit of a reminder. I'm going to pause for a second. How many groups of electrons do we have? So how many orbitals do we have to put together? We've got a single and a single, but then we got a lone pair and a lone pair. There are 4 groupings of electrons, so we need 4 orbitals to make those 4 groupings. So this is sp3 hybridized. It's the 3rd time we've seen sp3 hybridization. Bent angular V shape is 109.5. Every 20 needs to know this, okay? But you can connect it back to a tetrahedral type shape of electrons to get that bond angle. Okay? Because the electrons aren't atoms, we don't call it tetrahedral anymore. Okay? So I'm going to use patterns to just throw up a few other examples. I could switch to sulfur. It's going to bond the same way. So sulfur dihydride, same thing. Group 6 with something. I could switch that to fluorine, which has 1 bond, and the sulfur is still going to be bent. The lone pairs on the fluorine don't affect anything. Why don't they affect anything? Because we look at the central atom. The central atom has 2 bonds and 2 lone pairs. The fluorine atoms are not in the middle, so they're not affecting the shape. Okay. So that's our shapes. So at some point, you might want to make a summary like this to put in your notes, or do a unit review that has a summary like this. We have linear, we have trigonal planar, tetrahedral, trigonal pyramidal, and bent V-shaped. You need to realize something about the electron pairs. You can do a little diagram, and then you need to know the bond angles. Now, there's only 3 bond angles because there's only sp, sp2, and sp3 hybridization. Now, some of them show up more than once. So we're ending up with real bond angles. We're factoring in an order of electron repulsion. I'm going to call this real shapes. Most of your test is going to be just using VSEPR. Okay. Don't use this in all of your assessments, but you might get a question, order the following using real bond angles. That'd be your hint to tweak things a bit. Okay. So electron repulsion order. What's the greatest repulsion? Well, when the electrons are totally unblocked or unshielded. Lone pairs against another lone pair, nothing blocking them, that angle is going to be a little wider than expected. So if you have two pairs of electrons and you're expecting 109.5 degrees between those two pairs of electrons, you're going to see a little bit greater than 109.5 as they repel each other a little bit more. Second in the ordering would be lone pair with a bonding pair. Okay. The least repulsion, less than we would expect, would be bonding pair, bonding pair. So we have a pair of electrons with an atom, a pair of electrons with an atom. We would expect 109.5 degrees from VSEPR, but the real bond angle is slightly less than 109.5. Okay. The middle can be hard to predict, but the lone pair more than expected, bonding pair less than expected, if there's lone pairs. Okay. If there are no lone pairs, we don't have to worry about any of this. If we have methane, everything in methane is just bonding pair. It's just going to be a tie all the way around. There's no extra repulsion in methane. But we would see it, some tweaking to the repulsion in ammonia, where we got a lone pair. We're going to see a little extra repulsion from the lone pairs to the bonds, and the bonds, the H's, the N to the H to the N, will be a little tighter. Then we're going to do a ranking example to end this, and with some practical examples. I'm going to compare and rank the bond angles in methane, water, and C2H2, which would be ethine, a Chem 30 vocabulary term. So we've got 3 molecules to rank. I'm going to draw them first, and then we'll figure out the angles we have in each. So methane, that's tetrahedral, 4 bonds, no lone pairs. We've got water. Okay. Soon as I see sulfur or oxygen, I'm thinking bent or angular or V-shaped, because that's what group 6 tends to do. Now I'm going to stick in the lone pairs. The structural diagram wouldn't have them, but we want the lone pairs to cue our brains about all the type of things that lone pairs do, affecting the shape, tweaking the real bond angles. Last, we have ethine. We've got 2 carbons. Those carbons are going to each have 3 more bonds, 6 in total, but we only have 2 H's. If I do a double, each carbon has 2 bonds left. That's still too many. I'm going to have to do a triple bond. When I throw in the triple, now each carbon has 1 left. And that's going to work. That's going to give a duet for the hydrogen and an octet for the carbon. Next, after a little pause, I'm going to put in all the bond angles. I'm going to do the first one. That is 4 bonds, no lone pairs. that is tetrahedral. So we would start with 109.5. And I have no lone pairs there. So there's not going to be any tweaking to the real bond angle. So that is going to be straight up 109.5. Okay. Nothing to alter. Okay. Everything is equal. Okay. Water does not have everything equal. We got lone pairs, so we're going to have to tweak the bond angle. We're going to start with bent, angular, or V-shaped, which there's 4 groupings of electrons. So we would start with that same 109.5. And then we want to tweak the bond angle. Now, we are only concerned about that red bond angle. We don't do bond angles of the electrons, just H to O to H. VSEPR says 109.5, but that's going to either be expanded or squished. Okay. 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 We've got a bond to another bond. That's the lowest repulsion. Okay. The top electrons are going to get repelled out from each other, which is going to squish our H to O compared to the other H to O. So we're going to get slightly less than 109.5. Okay. Our bond angle, which I put in red, is our lowest of our repulsion, bonding pair to bonding pair. So that's why I went less than 109.5. Our last bond angle, we've got 2 of them. That first one has 2 bonds, no lone pairs, so that would be straight. And there's no lone pairs to tweak this, so it's just straight. If we look at this carbon, it's the same thing. 2 bonds, no lone pairs. It would be straight, and there's no lone pairs to tweak it. So we only had water that we could alter the VSEPR theory a little bit. So we can answer our question once we reread it. Rank the following from greatest, so biggest to smallest. So the biggest bond angle is our 180. The second biggest would be 109.5. The third, the smallest, would be less than 109.5. Water tends to be around 105, is what we see when we measure it in real life. 109, less a bit. You don't have to memorize that 105, but you should know it's less than 109.5. So that's our last question. So that's VSEPR theory. We're almost done. Once we know the shapes, we can start talking about polarity in the molecule. Is there a positive end and a negative end to this whole shape? If there's a positive and negative end, the molecule will be polar. If there's no positive and negative end, it will be a non-polar molecule. And this affects boiling points and melting points. Something polar is going to want to stick to its neighbor that's polar. Think a little magnet sticking together. Things that are non-polar aren't going to stick together very well, and they're going to have lower boiling points. It affects a lot of their properties.